Let's look at rocket propulsion. How is a rocket pushed up? That's what we're looking at. So I'll explain what exactly we are doing over here. First, for that, we have to go to the diagram. We have a rocket, and this pink color thing is your fuel, for example. So we started off with m naught amount of fuel, and say the rocket has some velocity. I mean, it need not have any velocity, but for the sake of conversation, I'll just take it as v naught, v r naught. So in time, the mass reduced to m. So basically, we are transitioning from m naught to m. So basically, m naught minus m amount of fuel got consumed, and this rocket gained a velocity of vr. Okay, by of course, gas being emitted out of the other end. Okay, let me put it this way. When you burn the gas, it will expand and it wants to go out. It's redirected in such a way that it is pointed downwards. And this leads to this rocket getting pushed up. Right? That's the whole funda of your propulsion system. So this is after t seconds. So from here, we went over here. And now we're looking at t plus delta t. After some very small amount of time, what happens? There's a small amount of velocity that is changed. For this, we have used up a gas whose mass is delta m, which is moving with a velocity of vg. Everywhere the gas exits with a velocity of vg. What is the left out gas? We had m, we consumed m, delta m. So left out gas is m minus delta m. That's it. Okay. So this is where we are at. Now, what is that we are exactly doing over here? Let me explain it this way. We are trying to get an expression for VR in terms of what gas we had, how much gas we have now. So basically, how much gas we have used up. So for that much of gas, what is the velocity we have obtained at this time period? So we are looking at this, trying to get an expression for the velocity of the rocket by understanding or making use of how much fuel we had and how much fuel we have. Based on this set of variables and few more set of variables, we are trying to look at what is the velocity gained by the rocket. Okay, so we're trying to get an expression for VR in terms of m naught and m and t and so on and so forth. Okay, now let me read the write-up. So now again, I'll start the head from the starting. That is the heading, sorry. So let's start from the heading. So in this video, we'll be looking at rocket propulsion. Rocket propulsion is caused by gases at higher temperature and pressure are produced by the combustion of fuel. They escape with a large constant velocity through the nozzle. So right, nozzles are generally in this way and they exit. The large backward momentum of a gas imparts an equal forward momentum to the rocket. This is as per Newton's third law. Right? The gas you burn, they have to go somewhere because it's expanded, it has less space. So it will be redirected such that they go down or opposite to the movement of the rocket. With decrease in the mass of the rocket fuel system, the acceleration of the rocket keeps on increasing. Right? Means what? Means we are using up the gas, means we are burning it. This burning leads to force because the gas has to go out. So Newton's third law and so on and so forth, and it leads to acceleration. There's force and so it leads to acceleration. One more thing that we're considering is that we are using the rocket fuel at a constant rate. So everywhere the rocket is going out at a rate of Vg. I hope you guys understood this diagram because after this it's just a matter of few steps and we are done. Okay, I hope you guys have a good idea of what we are doing over here. Now, let's start off with this being our initial case and this being our final case. So we're going to make use of conservation of momentum. So we know that initial is equal to final, law of conservation of momentum. Okay, given an isolated system, here the force is such a large force that we can ignore any air and all of that. Okay, so we can ignore that. So air drag or air, wind and all of those, we can ignore those forces. So when we ignore all of those forces and we are looking at momentum over here and momentum over here, it has to be conserved as per law of conservation of momentum. Right, the system's momentum has to be conserved when there is no external force acting on it. Right, so that being your initial. So what is that we are looking at? We are looking at VR or mass of m moving at a velocity of VR. Mass of m moving at a velocity of VR. Right? That's our initial momentum. Final momentum is what? We have VR plus delta VR, or actually I should go this way. We have m minus delta m moving with the velocity of VR plus delta VR, right? What else? We also have VG, which is going downwards, VG, or I can tell it this way. We also have delta M moving downwards. Let me make negative over here. Moving downwards. This is the total mass, right? M minus delta M plus delta M gives us M. So this system is same as this system. Initial momentum is equal to final momentum. Do you guys agree? A bit of simplification as promised. mvr plus m delta vr, then minus delta m vr minus delta m times of delta vr minus delta m vg. So anything that we can cancel and stuff, I can see this getting cancelled and nothing else. And one more thing is we can take up this, write a statement. Consider the term delta M delta VR. The values of delta M and delta VR are so small that their product can be approximated to 0. Because this is so small, like let me give an example. If I have 0.0005 into 0.000002 or 25 or 253, okay, some number like this, what do you end up with? A very small number. Can I approximately tell it to be 0? We can, right? So that is the case. So this 2 is 0. So we have 0 is equal to m delta VR, that is some value, positive value, minus delta m times of VR minus delta m, delta m VG. Okay, a bit of rearrangement, and we have delta m delta VR is equal to delta m is common between these two, and we have VR plus VG. What is VR plus VG? For that you have to go back to this diagram. What is VR plus VG? Go to this diagram. Go to this diagram, have a look at it. VR is over here, VG is over here. I'll give you guys a clue. Figure out the velocity of the gas with respect to the rocket, or velocity of rocket with respect to the gas. Can you find that out? So velocity of gas with respect to rocket will be velocity of the gas, that is minus Vg, minus of velocity of the rocket, that is plus Vr. So minus Vg minus Vr, or minus of Vg minus plus Vr, or if I transpose and all of that, I'll get minus Vgr. So let me write it over here. But Vr plus Vg is minus Vgr. That is velocity of gas. Again, this is relative velocity. This you guys have to be clear with by now with respect to rocket. Okay, so that I'll substitute. Okay, I'll do it here itself. M delta Vr is equal to minus delta M Pgr. Now, for a small time frame, right, but tending to 0, your delta Vr will become dVr, sorry. And your delta M tends to dm. And now bit of rearrangement. M dVr, actually more than rearrangement, just writing this. Okay, now I'll rearrange it. So we have dVr by Vgr, okay, is equal to dm by m. Yeah. So what is the, okay, let us integrate it with respect to some values. When time is 0, when the rocket just started off, we assume that it had a velocity of Vr comma naught and a mass of m naught, right? Okay, and at a time of t, the velocity of the rocket is Vr and the mass of the fuel is m. Again, I'm going back to this diagram. I told you now, this diagram is what we're going to use. Remember, we are trying to get an experiment for Vr. Then, on integrating both sides, integrating both sides, what we have is 1 by Vgr, because it's a constant, Vr naught and Vr, dVr is equal to negative m naught m dm by m, and 1 by Vgr, and this would be Vr. Again, I hope you guys are thorough with your integration. And this will be minus of natural log of m minus natural log of m naught. Again, this is to do with log. So if you're thorough with log, you know that this will be is equal to Vgr, bit of rearrangement. Okay, yes. So L log of m minus log of m naught will be log of m by n. Because there is a negative, that result will flip and you have this. If what I just told didn't make sense, let me write the formula. Log of a minus log of b is log of a by b. And one more formula that you need to know is negative log of m is same as log of 1 by m. Again, if you don't know all of this, you need to learn log. If not, well, you're at the wrong place as of now. So finally, we have Vr, or velocity after burning so much of fuel, will be obviously Vr naught. We already have gained that velocity at time 0. Natural log of m naught by m. That's it. Okay. Right, guys. So after a time interval of t, if you have burned so much, actually it doesn't matter what time we have taken. If you burned so much of mass, from here to here, if you got, the difference is the burning aspect, you would gain this velocity, a simple expression, right? Now, what if we burn out the entire fuel? Okay, so what if we burn out the entire fuel? So we have burn out speed of the rocket. So it's a speed that is acquired by the entire of the rocket. The fuel, total fuel is burnt out. So all fuel burnt out. Okay. So but the rocket, the entire thing, payload or including the structure, I forgot. I had the name in my. I just remembered it. I forgot. Wait. No, it is. Okay, I forgot, guys. So basically, the rocket residual mass is one technical word, but let's looking at some other word. The residual mass of the rocket, basically the physical structure, which is left out after the entire fuel is burnt out. Burnt. BM, I don't know. B, I guess, or whatever. BL, right? Then what we have is VR, okay, will be the maximum velocity, right? So that will be equal to VR comma naught. This will not change because, well, that is so. VGR, natural log of M naught by MB. That's it. So basically, this is the mass of. I want to tell one word, but I don't think I'm right in that. So let me not tell it. So this is the maximum fuel that the rocket will gain. A small expression, a small substitution. Actually, you don't need to memorize this. But yeah, you need to know the word burnt out fuel. I think there's an hyphen. It's a single word. One more expression that we have is thrust, I guess. Thrust of the rocket. Thrust has to do with your force, right? So force, how will we figure out force? For that, we have to go back to this expression. Okay, M, let me copy that off. So how can we do it from here? You have it in front of you, actually. It's very simple. How do we proceed from this? You can call it from 1. You can call that as 1, okay? Then we'll divide dt on both sides. And we have m dvr by dt minus vgr dm by dt, right? This is nothing but your acceleration. Okay. dm by dt, that is the rate at which you are burning the fuel. But what is this? That's nothing but your force. So basically this is equal to, obviously it will be opposite of VGR, that's right. This is dm by dt. So the rate at which you burn the fuel will give you the thrust. That is common sense. If you burn more fuel, you will get more thrust. Okay, all these are simple expression. Don't memorize any one of this. All this has to be commonsensical. Actually, it's a very simple derivation. The writing is a lot, that I agree, but yeah. Understand this diagram, you're pretty much done. Understand integration, understand differentiation. If this is like a simple algebraic, derivation.